This is the video discussion for Chapter 3 entitled Software is Everywhere. In this chapter, we are to explain the value of computer programs. We'll look into the use of Raspberry Pi for simple applications and Packet Tracer to model IoT systems. Programming, first part in Chapter 3. A program is a set of ordered instructions created to accomplish a specific task. Based on that definition, many everyday life activities can be seen as programs. All computers need programs. A computer is any device containing a CPU, memory, and I/O devices like monitor, keyboard, mouse, audio card, etc. Desktop computers, smartphones, tablets, digital watch, and smart devices are just a few examples of computers. And even though computers are everywhere, they are useless until they have running programs. Computer programs take many different forms, like operating system or a firmware or applications. These are examples of programs found in a computer. An operating system is a program which allows users to interact with computers and application software. Modern operating system has graphical interface like what we have in Windows or some variants of Linux and Apple iOS, mobile operating system like iOS and Android. Firmware are programs created to allow a computer to perform a specific task. Firmware is often found in small computers like digital watch or modern appliances and various subsystems found in modern cars. And due to limited memory and other restrictions, IoT devices often rely on firmware for their operations. Firmware and operating system functionality often overlap, and in some instances, firmware can also act as an operating system for simpler computers. Applications are programs created to help the user performing a specific task, like what we have in Microsoft Office with the Word, Excel, or a Firefox, a browser, and a calculator. People who can code are becoming more and more valuable in the current job market. We call them as programmers, and while these programmers were somewhat limited to desktop application coding in the past, the rise of the IoT is creating new possibilities for programmers. So in 1991, Mark Weiser wrote a paper entitled The Computer of the 21st Century. And in this paper, he envisioned the future of the IoT described as specialized elements of hardware and software connected by wires, radio waves, and infrared, and it will be so ubiquitous, like you can connect everywhere, or can connect any device so that no one will notice their presence. So in a world that is becoming increasingly digital, the ubiquitous nature of computing means that software is everywhere. Today, programmers may work on firmware or device drivers or mobile app or web interface, and including data analysis. So these employment areas were all available before, but the IoT has drastically increased the number of available projects and companies. Another benefit of being able to code is that programmers can create their own software tools. Need a specific network filter not available in the market. Maybe a project requires some specific data analysis, and this can all be coded by a good programmer. So what makes up a program? Usually, programs allow people to impart logic to computers and are made out of logic structures. So like example, mga conditional statements. So there's also these two types in a program. We have this interpreted versus the compiled. You're familiar with. Example, with web browsing, with HTML, that is automatically, the codes are automatically interpreted by the browser, while you're in your C Sharp, C++, it needs to be compiled, right? During this compilation, you compile is that this is the part where the codes are being interpreted, okay, being understood by your programming language. So, and again, there are different programming languages like JavaScript or Python or Blockly or C on Java. A common application for IoT system is data collection. IoT devices such as sensors are often deployed in locations where data collection is to take place. Agriculture, transportation, and manufacturing are just a few examples of areas where data collection is done by one or more IoT systems. While data collection is important, data must be processed before it can be useful. Collected data can be processed close to the point of collection, or it can be transmitted and stored in the cloud for processing at a later time. Often, data from several sources is combined to provide the most useful information. Computer programs are used for the efficient processing of the collected data. In transportation, for example, data such as the number of trucks using a specific stretch of highway or the temperature of that section of pavement and winter tire and gas prices can be collected. And data processing can tell when to install winter tires on the trucks based on the days the roads are frozen. And there are many again languages supported by an IoT system that can be used to create computer programs like Python, for example. So an important aspect of an IoT system is its ability to make decisions, triggering an alarm if carbon dioxide levels across a threshold, or unlocking a door upon detection of the correct key fob are two examples of decisions that can be made or could be made by IoT devices. Some IoT devices are also capable of more complex decisions, making such identifying a person's face from a camera feed. The ability to make decisions can be added to some IoT devices via software. Programs must be written and uploaded to the IoT device for execution before the device can make any decisions. In many instances, programs need to communicate with other programs or websites or devices. So you need to have like an API in this case, which again stands for Application Program Interface, which I think at this point you are familiar with. The way we define this the way we define this is that this is a set of routines and software tools that facilitate communication between programs. And we are thankful to APIs because application running across the networks can communicate between each other. You can share data and ask for specific services from other applications. Different types of APIs are available, including operating system API or say an application API or a website API. So example, let's say when creating a file manager application, a software developer will take advantage of the operating system API to copy, move, or delete a file. And if the developer's application does not have the necessary code to perform these functions, then it can simply ask the operating system to perform them through its exposed operating system API. IoT applications can talk to each other using APIs, but they can also use APIs to talk to various cloud-based services. Representation state transfer or REST or RESTful web services. This is a type of API designed to make it easier for programs to interact over the internet. REST APIs uses HTTP-based calls between different applications to access and manipulate information stored within powerful databases. Web resources used to be identified exclusively by a URL. Um, and today, web resources encompass every entity or thing that can be named, identified, or addressed. Entities could be a day step goal, temperature setting from your house, or heart rate from a pacemaker. Each resource now has a unique URL, typically beginning with a slash, let's say such as slash heart rate. And REST APIs use the HTTP protocol and either URLs to create web services. Such REST web-based requests trigger responses in well-defined web formats such as XML or JSON. And by using HTTP as a protocol, RESTful services can borrow HTTP's operation, including the HTTP verbs like get, post, put, and delete. So an example could be a pacemaker sending updates above about your average heart rate to a medical database. So the pacemaker can use a REST API call in a specific format to update the information in the database. So IoT system can that take advantage of cloud services often rely on RESTful services to communicate. As an example, consider a smartwatch with weather capabilities where an IoT device collects weather information for its current location and display it to the user. And this watch could be programmed to communicate with a web-based weather system through an exposed REST API URL. An IoT system consists of the interconnection of several functional blocks: the devices, the gateways, the network, the cloud, and the actual application. On each of these blocks, there is code running to fulfill the function it has been designed for. Recommended best practices for securing connected devices in the IoT must include devices should protect themselves from attack that impairs its function or allow it to be used for unintended purposes without authorization. Another is devices should protect the private authentication credentials and key material from disclosure to unauthorized parties. And then third is devices should protect the information received, transmitted, or stored locally on the device from inappropriate disclosure to unauthorized parties. And the next is devices should protect themselves from being used as a vector to attack other devices or hosts on the internet. In order to help achieve the recommended security best practices, physical security and the ability to trust the integrity of the code and the ability to be upgraded remotely are crucial to the design of all systems and IoT devices. IoT devices are located in traditional locations like data centers in the cloud or also in many non-traditional locations, even like in light posts or parking lots and even in people's bodies. Traditional locations can be protected by surveillance camera or access control systems or biometric identification or multiple authentication points. Securing IoT devices in non-traditional location is more difficult. Devices should be manufactured to be resistant to tampering, and they should be placed so that they are not obvious and they are very difficult to access. And while one should do their best to protect these devices physically, a determined hacker can still gain access. So physical security is a good practice. Another one way a hacker can change the function of a device is by accessing the device and disabling its function. So and then installing new software on the device and restarting it. So another way to protect the device is to ensure that the code on the device is the original code that was created. And this security measure can protect the device from attempts to change its function. So even if the physical security has been breached. This is done by cryptographically signing the original code and ensuring that the device will not start if the code is not signed. And this is the same approach used to assure the integrity and provenance of documents. There are several approaches emerging in the industry to cope with different angles of this problem, such as trusted computing or Cisco Secure Boot. As an example, for the iOS on a router, Cisco iOS in the router, the Cisco Trust Anchor and the Cisco Secure Boot, it checks the signed code to help ensure that the code running on the Cisco hardware platform, or let's say IoT, is authentic and unmodified, and establishing a hardware level of root of trust and an immutable device identity for the system to build on is important. The Raspberry Pi single board computer. The Raspberry Pi is an expensive, small computer. It has a number of USB ports that can be used to connect various devices, including keyboard, mouse, external drives, and cameras. Because it is a full computer in a package, the size of a credit card, in the size of a credit card, the RPi has become the choice of many IoT projects. The Pi 3, it shares the feature of the Pi 2, which is its predecessor, but adds adds specs on it, like it has a 1.2 gigahertz 64-bit quad-core CPU, an 802.11n wireless LAN, a Bluetooth of 4.1, a Bluetooth Low Energy. The RPI also includes a 40-pin header with GPIO. GPIO pins, it's short for general purpose input-output pins. They are extremely useful when interacting with the physical world, like with sensors, actuators, and switches. They can be connected to this GPIO and controlled by the code running on the RPI. So other RPI ports include audio out, SD card slots, or Ethernet port, or USB, also camera interface or display interface, and a micro USB connector. Um, this is created by the Raspberry Pi Foundation, and RPi was designed to be small and inexpensive or cheap. RPi can run a number of operating systems like Linux or Windows operating system. There are several ways to set up and use a Raspberry Pi. Physically connecting an HDMI screen, a USB keyboard and mouse, it turns the RPi into a general PC and allows a user to gain local physical access. Once an RPi-compatible operating system image has been downloaded to the microSD card, the RPi is ready for use. Traditionally, the Raspberry Pi can be used as a full-blown computer with a monitor, keyboard, and mouse. These are the steps for using the RPi as a computer with physical local access. So first step is to install an operating system image on the micro SD card. Next is to place the card in the micro SD card slot of the RPi. And then third is connect a USB keyboard and then connect a monitor using the HDMI port and then power the device with the power adapter. Alternatively, to use the RPi as an IoT device, one must be able to control it remotely over the network. Headless is the term used for servers that are solely remotely operated. While many headless setups are available, this course focuses on a customized solution called Prototyping Lab Application or PLApp. The PLApp allows access to the Raspberry Pi directly from the network. Headless access allows for operation without the need for a monitor or keyboard or mouse to be directly connected to the RPi. Modern computers can boot the system from external USB devices and SD cards. With the increase in popularity of larger and cheaper external cards, it is common to have an entire operating system installed in such cards. The Raspberry Pi 3 includes a micro SD card slot to be used as storage device for the system. Before the Raspberry Pi 3 can be used, an operating system must be installed on a micro SD card and then placed in the SD slot for booting. While there are a number of ways to install an operating system on a micro SD card, the most common is to use an image file. An image file is a single file containing an image of an entire file system. In that sense, the image file is an exact copy of everything that was in the file system, and it can be used to recreate the file system on other media. Common image file formats are like .iso or .img. Several options are available for image transfer tools. The one used in this course is part of the PLApp launcher. This is a customized image transfer tool that simplifies the deployment of images used in the course. And PLApp Launcher also manages the discovery and headless controls of the network connected to a Raspberry Pi. If a user is downloading an image without specialized PLApp tool, the user need to obtain the image file created by the manufacturer or the maintainer who makes it available for download. The user can then simply download it from the proper website. The Raspberry Pi Foundation provides an image of Raspbian. This is a variation of Debian Linux customized for the Raspberry Pi. Many different shells were created and many features were added to facilitate typing and user interaction. Some of the important shell features include tab key file name and command completion, command history, keyboard shortcuts for moving through a command line, and others. Among the most popular shell are Bourne shell, Bash shell, C shell, improved C shell, Z shell. Which shell to use is a matter of preference for most users. Although a CLI is still present, the modern operating system often boots into the GUI by default, hiding the CLI from the user. One way to access the CLI in a GUI-based operating system is through a terminal emulator application. These applications provide user access to the shell and are often named as some variation of the word terminal. On Linux, popular terminal emulators are Terminator or eTerm or Xterm or Console and Genome Terminal. Regardless of the terminal emulator used, the user still decides what shell to use within the terminal emulator application. A package manager, also known as package manager system, these are a set of software tools designed to facilitate the installation, removal, and upgrade of computer programs. Computer programs often rely on external programs called libraries to operate, and maintaining such programs and their libraries manually is not scalable for a system with a high number of installed programs. A package manager can help automate the process and reduce human error. Different operating systems include different package managers. Debian and its derivative include DPKG. It's short for Debian GNU Linux Package Manager. And to automate the process even further, users can use apt as a front end for DPKG, and Red Hat Linux and its derivative use RPM, Red Hat Package Manager, as the default package manager for Linux distribution. Another popular package manager is called Yum. It stands for Yellow Dog Updater Modified. Yum is capable of automatically tracking dependencies of a package and installing them prior to installing the package. A package manager usually includes user tools and a remote package repository. The user tools facilitate package management and can be a CLI or GUI. So the remote repository is used by the package maintainer to host the packages, and package managers are also very helpful for package versioning, allowing users to upgrade or downgrade a package or ignore a specific package version. Building models of IoT systems in Packet Tracer. Packet Tracer is not only a powerful tool for modeling or simulating and testing network environment, it can do the same also for IoT solutions. Like in the new version of Packet Tracer 7.0, it introduces support for a number of IoT devices and functionalities that make it possible to design and build complete IoT solution. Among the IoT devices supported by the Packet Tracer 7.0, it is possible to highlight programmable models of sensors, actuators, microcontrollers, single board computers, and fog computing devices. And this allows the design, configuration, programming, and troubleshooting of increasingly sophisticated models of IoT systems. A good example of what PT 7.0 can do with IoT simulation is like a smart home, similar to the figure shown here in the slide. Um, the model includes connected doors or garage doors, sprinklers, connected smoke detectors, ceiling fans, and more. All these can be controlled and monitored via web interface, accessible from any device in the home, such as a tablet, smartphone, or laptop. So PT 7.0 does all this while also representing the network underneath with wireless routers, switches, and cables. In a smart home example, all devices connect to the home gateway. The home gateway acts as a concentrator for all devices, providing wired and wireless connectivity. It is also the home gateway that a web interface is created and hosted to allow users to control and monitor all of the connected devices. In the model, sensors monitor the environment and make sure values stay within a predefined threshold. If the monitored value passes the defined threshold, an action is taken. So say the smoke detector, a sensor monitoring CO2 levels in the house, has a predefined value of zero point 0.4, and if the measured level surpasses zero point 0.4, the alarm goes off. The smoke detector has no user control functionality, It simply responds to the environment. Network connection between the home gateway and other network devices are also represented. So you notice how the home gateway connects to a cable modem, which in turn connects to a splitter, and the splitter breaks the signal coming from the ISP, sending cable TV signals to the TV and data to the cable modem. And then the cable modem and splitter is what internet connectivity to the home gateway and consequently to the entire home. And then, chapter summary. So again, programs are used in IoT to provide logic and intelligence to the devices. A programmer can create code to allow an IoT device to perform tasks like monitoring, communicating to others, and data processing and more. The RPI, a single board computer, is designed to be small and consume very little power. A Cisco PL app allows access to the RPI directly from the network without the need for a monitor, keyboard, or mouse to be directly connected to the Pi. The Raspberry Pi runs Raspbian. This is a modified version of the open source and widespread Linux operating system. The Raspberry Pi supports many different programming languages, including Blockly, a visual programming language designed to help beginners learn how to program, and with added support to Python, Cisco Packet Tracer is a great tool to model, prototype, and test entire IoT system. Ends this chapter. I'd like to thank you for listening. Keep safe. Together we learn as one.